language for extended pattern matching and binding Boolean expressions from Arthur Charguéraud and Yanni Lefki.
Thank you for the presentation. So, hello everyone. I'm Yanni Lefki, a PhD student at Inria, Strasbourg.
Well explained. Merci.
Ça va, ça allait.
The mic away from the.
Sure.
And no, it's not this issue. You can take it off if you want.
Sure.
Just keep the mic away from the speaker.
Yeah.
Okay.
Sorry. Anyway, so I'm a PhD student at the University of Strasbourg. Advised by Arthur Charguéraud, and I'm going to present some unification process for pattern matching called a core language for extended pattern matching and binding Boolean expressions. So, when talking about pattern matching, we have to speak into the microphone. So, in the microphone? Because, sure, okay. Tell me if there is any interference. Sure, okay. So, pattern matching is very old as ML actually. So, got created in the 70s. We have a lot of improvement along the years. So we had some exhaustiveness checking, efficient compilation scheme, first-class patterns, views and active patterns from Haskell and F#. At the time, maybe we thought that all the problems were solved, but in fact they were not, or there was no consensus on how to unify pattern matching. So more recently, we have the if-let construct from Rust, which allows for flowing bindings along the condition. And very recently, we had a work from Liu Cheng and Lionel Parot called Ultimate Conditional Syntax, which presents unifying syntax for pattern matching. Our work aims at pretty much the same thing, trying to provide a yet even slightly simpler syntax with the semantics and typing rules to go with it. So first, I will present a small two features that we would like to have in pattern matching that is not in every language. First is what we call smart deconstructors, or views for Haskell people, or active patterns for F# people. So say you are a compiler creator, crazy, right? And you want to write an AST. So an AST can be just a type with some meta information and a descriptor. The descriptor is just a list of constructs. So we have term bool, term if, term end. To build such a term, what you could do is just by hand write the element that we can see in the middle. Another thing what you could do is use what we call smart constructors, which are functions that will build them for you. So here we have the term if and term end function below. The use for smart constructors is to separate the actual library to the client code, which uses the library. And it allows us to modify the representation if you want, without breaking any code. So say we want to change the representation of term end and say it's just a particular case of an if, then we could do that by just removing the constructor and changing the function. So all good, there's no need to modify the code. However, let's say you want to pattern match on said data type. So if we want to recognize a term of some form, here a double conjunction, we would have to break the actual type using the constructors and return the subterms. This means that the client code mentions the actual implementation. This breaks the abstraction layer, meaning that if you do the actual modification I presented in the last slide, you will have to modify the actual client code. Also, there is a small lack of conciseness, because if we compare it to the actual creation of said term, which just uses twice the term end function, here we have to go deeper in the definition. So one may ask, why not just use the exact same syntax to deconstruct our term like we did to construct it? So in that case, we could just match on some term and by some magic inverse the creation of the term, and this would work as wanted. So in this syntax on the left, I reuse the same name as for the constructors, so term end here, but this would be considered some kind of pattern version of term end. So say we created a library of patterns, library of deconstructors, this would be part of it. So part of the say library, you could define all of the deconstructor versions of our functions. So one for term if, one for term bool, and one for term end, if you assume that we encoded it with the definition from before. So these functions will just return return an option with either none if it does not fit the form, or some with the subterm if it does. So let's put that aside for the moment and go to the second feature focus, which is tests that export bindings. So let's look at a very regular usage of hash tables, in which we just deconstruct some terms, check if it has some key, and check whether this key has some value bound to it in a hash table. If it does, you access it and compute with it. The small issue we have with this code is that we have two accesses to a hash table, meaning that it's not perfectly efficient. A little more efficient version, which is a little more painful to write, would be to use the getOpt function. However, in OCaml, you are not allowed to bind stuff out of a when clause, meaning that you would have to first look at the shape of T, and then inside of the continuation, use the getOpt function, meaning that you'd have two places that you could fail, meaning two possible continuations for failure, meaning that you will have to factorize it beforehand. So here again, why not just put the bindings in the when clause? We could just have some kind of Boolean operator, which will test an expression against some pattern. This operator is one construct of a kind that we will call binding Boolean expressions from now on, which the syntax will be detailed in the later slide. And this is just a construct that computes some expression and checks it against a pattern, and if this is correct, binds the values. So this could also appear in conditionals. This is a identical code with just an if, and inside the condition we have possible bindings to the then branch. All of that is not new. You also have this in the if-let chains I mentioned earlier in Rust. This is a code taken from one of the Rust RFCs, in which you have a chain of lets that matches some expression on the right and some patterns on the left of the equal, and you have a chain of them. Finally, this conditional also could be used in a while construct. Say you want to check inside of a queue and do a loop only until the queue is empty. Then you can check whether the queue is empty and then access it, but that's to access to your queue. You might want to just try, attempt to get the element from the queue, and if it doesn't work, you know when you stop. Here is a little more complex example, which uses the same principle for the merge operation of a merge sort. You just access the top of two stacks in the same condition, and if it works, you do your operation. Okay? So I promised some syntax, so let's go to it. Afterwards, we'll look at typing and semantic rules, and a compilation scheme to an ML-like, naive ML-like language to show that this is not magic. So, we start with grammar of terms, which is just lambda calculus, regular lambda calculus, to which we added a switch construct. The switch is written with a list of branches. All of those branches are cases with a binding Boolean expression as a condition, of which the syntax will be detailed later. And if the binding Boolean expression is considered correct, we get the result bindings and give them to the continuation. So we can encode the regular constructs of pattern matching, such as the match, for which we'll just use the is construct that will be detailed next slide, sorry, and that we've mentioned before, which tests some expression against a pattern. Since the T on the match is evaluated only once, we have to evaluate it first, but this is not that much of added code, so it's okay. For the if then else construct, this is similar. We test the condition in some case. If the case is true, we go to the then branch. If not, we go to a trivial true branch, and we're done. So for BBEs, we first have the is construct, which I've talked about earlier, which tests some expression against a pattern. There are also conjunction and disjunctions. The conjunction is a binding conjunction, meaning that you can test the first binding Boolean expression. If it is deemed correct, we get all of the result bindings to be used in the second one. This is exactly what we've talked about with the hash table thing. You test against some pattern, and if it is correct, you can follow through to the other one. Disjunction is as expected. You test against two BBEs, and if one of them is correct, you bind through, giving intersection. You can also have a negation of binding Boolean expression. This is also quite easy to understand. So in the T is P, we have a pattern, which has a syntax. So the three first constructs are fairly regular, with pattern variable, disjunction, and intersection. The when construct just asks for another condition on top of it, which is very similar to the OCaml when, but is allowed to be deeper than the top level. Also, we have what we call an inverser pattern and what is called view or active pattern, or we also call it deconstructors. It takes a function f, which is any function of the type t to some n-ary option, and will evaluate the given expression in some test. You evaluate the given expression f of x here. If you look at the encoding with when, you test f of x, and if f of x succeeds, you forward all of the result bindings into the asked patterns. So this allows you to have deep tests, such as the double term end that we saw a few slides ago. We also have some predicates that can just be seen as a particular version of an inverser pattern, because a Boolean is equivalent to having an option of unit. Just to be said, there is no loss at not having data constructors, since they are just trivial smart deconstructors. Okay, hypermodal typing and semantics. We have three typing judgments: one for term, which just gives a type to the term; one for binding Boolean expressions, which gives as type a map of all of the promised variables to the types. Sorry, so maps of the types to the bounded variables. For patterns, all the patterns are expected to be matched against something. we take T as the type of that something, the term that is matched against P, and B is, here again, the possible premise result bindings. We do not check for exhaustiveness, so this will be a problem for later. I mean, this will be something that we have to mention later. So the typing itself is fairly regular. Typing of a switch revolves on the typing of every branch. We need every branch to be of the same type. The type of a branch asks for the binding of the condition and takes the bindings of the condition and gives it to the term itself. The typing of an is construct for BBE asks for the type of the term, and if the term is of the correct type, feeds it to the pattern, and we return the result type. For the end here, the bindings of the first BBE is fed through to the second one, and we give the union as a result. Note that there is a disjointness operator. We ask for both of them to be disjoint since we disallow shadowing as an arbitrary choice. Finally, as a very small side note, we ask for both binding Boolean expressions on both sides of an OR construct to be of the same type of bindings. This is not a problem, as we will see in the next slide. We add a restrict construct that allows for scoping variables without, like, for free, to allow for some variables to be used as local computation inside of BBEs. This means that we could, again for free, before the typing process, compute the possible intersection of the binding of each BBE and just restrict both sides to remove any issue. To type patterns, all of that is fairly regular once again. The important rule is for the inverser pattern. Here again, we ask for the type to be some type to some n-array option. And we ask for every pattern to take the corresponding type as input and give a corresponding binding as output. If all of those corresponding bindings are disjoint, then we return the union. Okay. So we have typings. Now let's go to semantics, and then we will be done with rules. We have three judgments. Evaluation judgments for terms is regular again. We evaluate to some value. Evaluation result for BBEs and for patterns gives us some results R being either a mismatch if the match fails, or a match to some map, which maps variables to their corresponding bindings if the binding is correct. So all of the semantic rules will not mention mutable store, but we assume during our research that we could allow for some side effects. So we will have to look at, to be aware of order of execution, sorry. The execution of a switch construct just looks at the first condition. If the condition is deemed false, then we execute the rest and evaluate some value. If it is deemed correct, then we get the result bindings, substitute them to the continuation, and get the result. The test of a BBE takes the result binding of the expression and feeds it to the pattern. The evaluation of BBEs is quite standard again. The end construct is as advertised. If the first one is considered false, everything is false. If the first one is correct, then we look at the result of the substitution of the second one, meaning that we flow through all of the bindings. And if it is correct, then we return the union, assuming that both are disjoint. But if it is well typed, they probably are. For the OR construct and the restrict, this is quite okay in the sense that we test the first one, and if it works, we return it, and if it doesn't, we return the result of the second one. And for restrict, we just have an operation that will restrict the possible result bindings, if any. For patterns, here again, this is also regular. The when construct is the evaluation of the when construct is similar to the evaluation of the AND BBE. We feed through the possible bindings of the first check. If the first check succeeds, then we feed it to the second one. And if the second one succeeds as well, then we return the union. For inverse patterns, we evaluate f of v. And if the f of v evaluates to some tuple of values, then we check every value one-on-one and get the result bindings. And if it works, return the union. Finally, for the predicates, we just look at the results of the evaluation and either give a mismatch or match of empty, depending on if it is correct or not. We have a theoretical result for that, which is type preservation, meaning that if one term is well typed and does evaluate correctly to some value, then the value is of the advertised type. Similarly, for binding Boolean expressions, if a BBE evaluates to some bindings and there were some promised bindings, then those bindings, every variable bound, the value in every variable bound has the promised type from the typing. Here again, for patterns, this is fairly symmetrical. So, as a future work, we would like to give process. So, as I was saying earlier, we don't have any exhaustivity checking because of the when construct, there is an arbitrary deep evaluation of terms inside. So there is almost no way to know for sure perfectly whether we will reach or not the end of a switch construct. However, we could, and this is a work in progress, we could prove progress assuming that we do not exhaust any branch, or in other words, proving that the only way to fail is to exhaust branches. Finally, I said that we have theoretical results. Unfortunately, this result is only done on paper for the moment, but we are hoping to do that as a formalization on ROC as soon as possible. So I will end this talk with presentation of a naive compilation scheme to some easy ML-like language. So we have some translation operation. Here, the double bracket is the term in our new ML language. So double bracket of t is just translation of a term. Double bracket of some BBE with u and u prime represents the translation of some BBE with a success or a failure continuation, depending on its results. And similarly for patterns, when given some value, the evaluation result would be some continuation for failure or for success. Quickly, this translation is fairly mechanical and does not have very interesting technical details. We can just stress them a little bit. For the switch construct, we first evaluate the BBE as detailed by the order of evaluation. If it succeeds, go to the translation of the continuation, and if not, we go to the translation of the rest of the switch. Testing an is just evaluating the term first and then feeding it to the translation of the pattern. And finally, evaluating no, sorry, not finally. Evaluating a smart constructor is just getting the output of the translation of the function with the value and checking whether it fits some pattern. If it does, we check one by one every variable with its corresponding pattern. Finally, for the when, we do pretty much the same. Test P. If it succeeds, we test B. If it doesn't, we directly go to the failure. So we also have a theoretical result for that, which is the correctness of our translation. So we detail in the paper the syntax of the language as well as semantics. And we want to prove that if our source correctly evaluates with some conditions needed to have a strong enough induction hypothesis, then necessarily its translation will correctly evaluate. So, as a conclusion, first of all, for the future work, we would hope to have some formalization as soon as possible. As implementation, we have started to integrate all of that in the Optitus framework, which is an interactive source-to-source compilation scheme for functional languages and imperative C. All of that is only starting, so we would like to work on it. Also, maybe some preprocessing for OCaml. Although, since we designed a compilation scheme to ML, maybe we could preprocess and pass our syntax and feed it to an ML language like OCaml. And maybe, if possible, to have some conservative language extension. So, one feature that we do not for the moment hold is backtracking patterns. If we fail in some continuation, there is no way to come back to the next case. So we will have to commit to some case if it succeeds. So maybe we could add that with inspiration of exit blocks. And if any of you have any suggestion of programming patterns that we have not or might have not covered, I am very welcome to hear them. Thank you very much for listening to me.
Yeah, thank you for the talk. I think we have time for one quick question while the next speaker is setting up.
Oh, sorry.
Do you have...
I mean, I could ask several questions, but let me pick this one. So one thing that is interesting here. So as a programmer, I would like to have some of this feature. As a language designer, what bothers me a little bit is that you now have all this duplication, like your pattern language and your BBE sub-language. They seem to be very similar in structure, and I wonder if you have some ideas for like avoiding that duplication and maybe being able to express one in terms of the other.
So in fact, in the implementation, so in the very small implementation we have, all of them are the same type. Mm-hmm. And just with I'll just take the mics off. And all of them have the same type, just with like unwritten rule not to use them in another case. We think that we could, for example, use BBEs as some particular terms with a type says that it binds something. And since the patterns are very symmetrical, we also think, as you were asking, that we could take a pattern and just put it in the syntax of BBEs, just with some added prefix if needed.
Thanks.
All right, let's thank the speaker again.